All right. Hey, everybody. This is our first study group of phase 2. Wild that we're already like a quarter of the way through material. So congratulations. First of all, I wanted to talk about where you can find my comments on your project whenever that is in. So to find your comments, and by the way, you'll probably, I think, receive an email, depending if you've like edited your Canvas notification settings. You should receive an email whenever I've graded and marked your project as complete. And if it is incomplete, or if I find that there's something that you need to change, I will actually let you know either during our review or I'll Slack you and tell you. But if you receive this email, that means you've passed your project and you're good to go. So to find the feedback, you click into phase 1 project, and then you go to submission details. And then in submission details, you can see that on the top right, there's this show rubric. So you just have to go show rubric, and then you'll see on your version that I submit, there will be my comments. It'll show like in green whether you get 3, 2, or 1 points. There's no points for this project. It's just how the rubric is. But also you'll see like my comments under each relevant section. Or if it's overall comments, I'll have some overall comments. So for the most part, I usually just throw a bunch of comments in a bunch of these sections. Don't worry about the points. Also, just so you all are aware, I am a fairly easy grader in terms of as long as you meet these, and you can also see that these are pretty, what's the word? They're like very open to interpretation. So yes, I think for the most part, most of your things will be 3 points, but I will always put my comments and feedback on how you can improve if I see anything to put there. So just to let you all know. Cool. So that's on where to find my feedback. The next thing I wanted to talk about is blogs. So let me just leave the student view real quick and then go back to our blogs. So there is a blog post link here for you to submit your blog. The due date to submit your blog is just before we kick off the next project. And also like that deadline is not, you can pretty much submit your blog whenever you want. For the blog, you just have to write anything related to data science. What most people end up writing about is their project and their experience working on the project. So feel free to do that. If you remember on the guidelines doc on the guidelines doc, I've also put a link to my Medium account where you can see all the people that I follow, which are all Flatiron grads. So feel free if you want to get some inspiration on that. If you want to get some inspiration on that, that is there. And by the way, after I've changed this, all of our material will be in this Flatiron Resources Google Drive. So if you want to refer back to like the phase 1 doc, you can go into phase 1, click into the project 1 guidelines. I've actually reformatted and like added some more stuff. So feel free to go and check it out if you want. But if you scroll to the bottom, you'll see that you can find some blog examples here. This is my Medium and all the people that I follow. These are all Flatiron students. I think with the exception of like maybe like not more than 5 people. So feel free to click through and find blogs that if you're looking for inspiration. So that is blogs. It does say 800 to 1,000 words. I would say if you are not a writer, I'm also not a big writing person. If you're not big on writing, anything upwards of 500 words is good enough for me. All right, and you also have to write 4 blogs throughout this program. So remember, you have to write 4 blogs. I like to just throw them in between each of the projects. All right, so that is blogs. Before we get started on the new material, any questions?
Do you count stop words as words in that blog?
Yeah, they count. They count. Yeah, you can probably guess that I'm not very big on like these like little requirements that are not super like material focused. So yeah. Okay, let me reshare my screen so there are not those other tabs in the way. This study group, as well as the next 1, 2, 3, 4, 5, the next 11 through 15 will actually all be PDF slides that are on your repo. So they're all there. Oh, leading up to that, I wanted to mention one more thing. I do want to talk about phase 2 as a whole. So let me just go to student view real quick. So phase 2 as a whole, I forget what the name of the phase is, but it's basically stats leading up to linear regression. And so how phase 2 is structured is pretty interesting. The first 17 topics are statistics, probability and statistics, of which the most important thing that you need to get out of this is the ability to interpret what's coming later. So there's going to be a lot of statistics theory in this first 17 topics, but you very rarely will be asked to do straight up stats at a data science or data analyst job. So just be aware that there's going to be a good bit of statistical testing in these first 7 sections, but is not directly what you're going to be doing. A lot of the stuff that you'll see here, as an example, you'll come across like p-values, statistics, or like t-statistics, or hypothesis testing. You'll come across these terms. In these first 17 topics, you'll be asked to do like traditional statistics procedures, but you won't really need to do that at your job, very, very likely, unless you take more of a stats focused job. Rather, when we do linear regression is actually very statistically, it's very tied to statistics. So in linear regression, we'll see when we get there, they'll basically give you an output of like p-values, t-statistics, so on and so forth. And your job as a data scientist is to interpret that and use those results to guide how you build your models in the future. So you won't be doing statistics directly, although a lot of the exercises, topics 11 through 17 will be. On top of that, there is a good bit of math, and a lot of the coding in these topics are very much, okay, these are the formulas to calculate this, write a function that does this formula calculation, and then do that. And then at the end of it, they'll show you, hey, there's a library that does it for you. So be aware of that structure. You'll never be asked to hard code anything from scratch from memory. So don't worry about that, which is why I do think that the first 17 topics, especially, with the exception for like A/B testing has some code in there. With the exception of that, I don't think you have to worry about coding too much. It's really more conceptual. And on the topic of being conceptual, if you are wondering, okay, what are the concepts to focus on? I've linked a document, oops, wrong cohort. I've linked a document over here, this doc, which is a DS concept questions document. If you want to find this, if you want to find this in the Google Drive, it's actually under phase 5 because it does encompass a lot more stuff. So if you're excited, if you want to just see what's coming up, you can do that. But within statistics, these are the main things that you want to take away from the first 7 topics within phase 2. There's a lot in those 7 topics, but these are the main things that I've come across. And this document is derived from my own interviewer experience and my past students' interview experience. So if you want to like really narrow down and figure out, okay, what are the questions that I need to be able to answer at the end of this? These are the questions. And then when we get to linear regression, you'll see that some of these will come back as well. Any questions about phase 2 as a whole? All right, it's going to be very, very conceptual. So we'll prepare for that. Okay, let me throw this up here and let's get into topic 11, which is combinatorics and probability. There is probability and then there's statistics. Probability is the more, I guess, mathy way of just literally saying, okay, what's the chance of this happening out of this? And statistics is more of like doing like tests and stuff. And we'll get into that later. Probability is more similar to like fractions and ratios and stuff like that. So in this unit, we're talking about combinatorics and probability, which in itself is an entire college course. Like I took 2 semesters of just probability, not even statistics. So just be very aware that like this stuff can get really, really deep, and in like a single not even an hour, we're gonna pretty much get through an entire college semester's worth of stuff. So I'm gonna break down and tell you all what's important. Okay, so this is a quick agenda. We're gonna talk about what is probability and why we need it. And these are the main keywords. We're gonna talk about set theory, permutations, factorials, combinations, and then the one that's going to carry forward into our machine learning is going to be more conditional probability and law of total probability. So to start, what is probability? I think that is a word that we use a lot. I think one word that we get people tend to use like interchangeably, but we'll actually see later. The word odds and probability actually mean completely different things in like a math sense, and also I think in like a gambling sense. Not too sure about that, but yeah, the one of the formal definitions for probability is the probability of something occurring is its proportion of all possible outcomes. So let's say we have a 6-sided dice. Roll the dice. What's the probability of it coming up as a 1 out of 6? If you want to go to even more mathematical formal definitions, a probability of something occurring is the event space divided by its sample space. So a sample space is all possible outcomes. Sample space refers to anything that can possibly happen. So if you're rolling a 6-sided dice, 1, 2, 3, 4, 5, 6, you have 6 possible outcomes. And the event space, which is what you're finding the probability of, the event space is what you're trying to find the probability of. So if you're trying to find the probability of rolling a 1, it's just 1 divided by 6. So for example, probability of flipping a heads on a coin, on a fair coin, it's 1 out of 2 because heads divided by heads and tails. Rolling a 5, 1 out of 6, so on and so forth. Why is this important? Statistics is built on probability. And also in terms of data science application, once in a while you will get probability questions. I will say this is more in the case of if you're going for more like quantitative roles, if you're expected to do more algorithm stuff, which we'll get into like next phase. But yeah, only then you'll get probability questions, because other than that, it will be more related to statistics, more related to specific machine learning modeling things. Probability questions, it does come up once in a while. There's one particular machine learning model that is built purely off of probability, but we'll worry about that later. But just for context, probability doesn't come up too much, but it is important to understand the main principles that are behind probability. Okay, so set theory. The main thing to get out of set theory is the terminology. So if you have 2 sets of things happening, there's the union, intersection, and the complement. So as an example, and let me just grab my little Zoom pencil here. Okay, so let's say we have the left circle is A and the right circle is B. So in A, and let's just use like numbers from like 1 to 6. So let's say in A, we have the numbers 1, 2, 3. And in B, we have the numbers 2, 4, 6. These are just some predefined sets of numbers in this space. So let's just say that our entire sample space is the numbers 1 through 6. So there are some numbers that are represented here, some numbers that aren't. This is called a Venn diagram, which is a pretty common way to represent small numbers of probabilities. So in a Venn diagram, there's a rectangle with a bunch of circles that represent different events. The rectangle is the event space. So the rectangle is actually important. Whenever you draw a Venn diagram, it's actually important that you draw a rectangle encompassing the 2 circles. And because it represents our sample space. So I actually like to, whenever I'm presented with a Venn diagram kind of question, and I'll actually send you all like a recording of me going through probability questions if y'all are interested in. I will say it's probably one of the less important things for now, but in case you're interested, I'll send it out. So first, when I'm presented with a Venn diagram question, I like to label it as much as possible, just so it's easy for me to refer to things. So given this diagram, and let's ignore the other two for now. Let's talk about this union example. 1, 2, 3 is in A, 2, 4, 6 is in B. What is overlapping? 2 is overlapping. So I would actually put 2 in the middle here. And I would put 1, 3, 4, 6. And then 5, which wasn't represented, actually belongs outside here. So for our entire sample space of the numbers 1 through 6, this is how you represent it. And so union basically looks at the combination of everything that is in A and B. So if there's a question of like, okay, what is A union B? And the notation for that would be A U B. A union B would actually be 1, 2, 3, 4, 5. Oh, sorry, 1, 2, 3, 4, 6. 1, 2, 3, 4, 6 is the union. So similarly, let's just like transplant all these numbers again. What is the intersect? The intersection is basically the ones that overlap. And so in this case, the number 2 is the only one that appears in both A and B. And the notation looks like this. It's an upside down union. So just in case you come across this notation, this is only the number 2. There we go. And then lastly, complement. Complement, it is a little bit trickier to understand. So let's just say that this circle here is A, right? So this circle is A. What is A complement? So inside A, we have 1, 3, and 2. The complement of A, and there are several different ways to notate it. One way is with a little apostrophe. Another way to notate it is with a little C on the top for complement. So either of these mean complement. And the complement is actually anything in the entire sample set or in the entire sample space that isn't in A. So it's actually not just this green part, but it's also the 5 that was out here. So the complement of A is actually 4, 5, and 6. Specifically, how would we, like, if we want to like get to this green part, you can actually do what is the complement of, hold on, let's see if I can get this. What is the complement of A union, let's see, A union, like the number 5, for example. So with A union 5, the complement of that, because A is here, the 5 is out here, complement of that would be this green part. There are other ways to write it, but if you want to get to this specific thing, that's one way to do it. Let's see, I think another way to do it is like, yeah, I won't get into that. We don't need to get so into set theory for now. But yeah, that is set theory. I would say like the main things, union, intersection, complement, just know roughly what those mean. Often if you have a question that has you working through these kinds of things, it's pretty straightforward. But sometimes hard to get used to just seeing different symbols for notation. All right. So yeah, terminology from before. Sample space is all possible outcomes. Event space is the subset of a sample space based on probabilities we want to calculate. There is a law of relative frequency. I would say definitions, not important to remember at all. But these laws and these like these formulas that we're going to talk about in a little bit, they just help you to, I guess, verbalize some of the things that we notice in probability. So the law of relative frequency actually helps determine and helps define what it means when we say, okay, the probability of rolling a 1 on a 6-sided die is 1 out of 6. So law of relative frequency actually says that the probability of an event is the ratio of positive trials to the total number of trials as we do an infinite number of trials. So what this means is, sure, we have 6 sides on a dice, but the idea of how probability comes about through the law of relative frequency is if you were to take a dice and roll it an infinite number of times, the ratio of it coming out as a 1 is 1 out of 6. So that's where they get to the idea of law of relative frequency and how they come to probabilities. You can actually conduct, I think like when I was in college, I did this experiment where I actually coded something out. I think you can do, I think there's a lab that does that as well. But if you just code like a random number picker from like 1 through 6, and you calculate the number of times that it comes up as 1, it starts off not being exactly 1 out of 6. Let's say you do like maybe you do it like 10 times, 100 times. The more times you do it, the closer the ratio gets to 1 out of 6. So that's the whole idea of probability, using the law of relative frequency. So that's just one way that you can help think about probability a little bit. All right, next there are some probability axioms. Again, not important to memorize this, but good to know because this helps us just remember some probability facts. So first of all, the probability of an event is always between and inclusive of 0 to 1. So the smallest probability you can have of anything is 0, and the largest probability you can have of anything is 1. Any probability has to be between and including 0 and 1. A certain event. So if you have an event that is equivalent to the sample space, the probability is 1. An example of this, or example of a certain event, is what is the probability of rolling a number between 1 and 6 on a 6-sided die? Now that is a certain event, and the probability of that is 1. And then there's additivity. The probability of the union of 2 exclusive events is equal to the probability of both events only if the intersection is 0. One quick way to demonstrate that, let me look for something with space. Actually, no, let me just draw it real quick here. So let's just say we had those like, let's just say we have a Venn diagram. And instead of our earlier example, we have even numbers, odd numbers. So we have even numbers here, odd numbers here. And so let's just say 2, 4, 6, 1, 3, 5. So the probability of the union of 2 exclusive events, and exclusive events is the main thing here, is equal to the probability of the event 1 and probability of event 2. So let's just say there's nothing outside the circles. Here we have 2, 4, 6, and here we have 1, 3, 5. With just these 6 numbers, we know that the probability of even, and the way that you write it is like this, probability of even is 1/2. Probability of odd is also 1/2. And in this case, the probability of the union of these two, and the union of these two is basically this area plus this area, both of which is 1/2, so therefore equals to 1. Probability of this plus this will work out only if these two do not intersect. So only if these 2 circles do not overlap. So it kind of makes sense. If they do overlap, there's a formula for that. Probability of A union B, if there's an overlap, is A plus B minus the intersect. And we can actually go back and look at our last example. So we go back and look at, oh, my mouse is not clicking. Okay. We go back and look at this. If we have our 1, 2, 3, 4, 6, 5, the probability of, let's call this A, let's call this B, probability of A is 0.5 or half, 0.5. And the probability of B is also 0.5, right? But what is the probability of A and B? Because the two, it overlaps over the 2, you cannot just add them together because you're double counting the 2, right? And so therefore it is not 0.5 plus 0.5. It's definitely not 1 because we have this 5 out here. So the that theorem was basically to find the intersect, to find the probability of the union, you have to minus the intersect. So basically it is probability of A plus probability of B minus the probability of the intersect, which is 0.5 plus 0.5, so that's 1, minus the intersect, and it is, the 2 is the intersect, which is 1 out of 6. 1 out of 6, so therefore the probability of the intersect is 5 out of 6. Sure, this is a formula. You could have also counted, okay, there's 6 numbers, 5 of them are in the shaded area, 5 out of 6. But if something gets more complicated, that's the formula you use. And the reason for that is because you don't want to double count things. All right, again, formula is not important to remember. but that's the intuition behind it. Okay, so we talked about probability set theory. That's one kind of probability. The next big, I guess, section of probability we're talking about is counting. And counting sounds like it's an easy thing, but factorials, permutations, combinations all fall under the framework of counting. And so you'll sort of see why in a little bit. So first let's talk about factorials. Factorials are denoted with exclamation points. And basically a factorial of a number is the product of all positive integers leading up to the number. So this is a formula, n factorial will give you 1 times 2 times 3 times blah, 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 all the way to times n. Basically that's saying that if I had the number 4 factorial equals to 1 times 2 times 3 times 4, which is 24. So that's what a factorial is. It's a definitely very, very common mathematical way of multiplying numbers. So anytime you see an exclamation mark with a number, that's what's happening. Probability use case. If you want to find the number of ways to arrange a certain number of objects, you find the factorial. So if I have the letters A, B, and C, and you want to think of, okay, how many unique ways can I arrange the letters A, B, and C? It actually evaluates out to 3 factorial because there are 3 unique letters. There are 1 times 2 times 3, which is 6. There are 6 different ways to arrange these 3 letters. And it does scale. If you have like 6 different things that you want to find the arrangement of that, you'll find that there are, let's see, what's 6 factorial? I think it is 720. There's 720 ways that you can arrange 6 objects. So that's a use case of factorials in counting. And figuring out like these arrangements and different numbers of ways you can get these kinds of things is important for calculating some probabilities sometimes. So that's good to know. Number of ways to arrange n objects. That's when you use a factorial. That's something that's good to remember if you are wanting to remember probability things. From factorials, we talk about permutations. So permutations on top of factorials, and later we're going to talk about combinations. These are counting methods that help us find the size of our probability spaces. So as I mentioned, finding these like numbers of ways to arrange or numbers of ways to like get a subset of things, that's going to be important to calculating probabilities. So permutations. Whereas with factorials, it was the number of ways to arrange a number of objects. Permutation is a number of ways to arrange k out of n items. So the formula for a permutation is n factorial divided by n minus k factorial. And I have an example. So let's just say that a band has a catalog of 8 songs, but has to play a set of 3 songs for, I don't know, a concert. How many different 3-song sets are there? And a different order of the same songs counts as a different set. So let's say they have songs A, B, C, D, E, F, G, H, 8 songs. They can play ABC, they can play D, E, F, they can play ABC is different from BAC in a permutation. So to find the number of ways to play 3 songs out of 8 songs, you want to use a permutation. And the formula for that, n factorial divided by n minus k factorial. N is the total number of things that you have, and k is the smaller number, the subset. So in this case, we want to take 8 factorial divided by 8 minus 3, so 5 factorial, which is actually equal to 336. Another way to think about factorial, if you want to think about it from like a fraction math way. So this, well, let me get my pen. I want to change the color also. Okay, let's just say we have 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, right? That's our 8 factorial times 7 times 8. Cool. And then when we divide, it's starting to look like plus, so I want to look like times. Okay. Divided by 1 times 2 times 3 times 4 times 5. That's what we're doing here. times 4 times 5. If you remember, I don't know, high school math, I think, if you have a fraction that looks like this, you can actually cancel out numbers. So how you can simplify this a little bit is you can actually cancel the 1, cancel the 2, cancel the 3, cancel 4, and cancel the 5. And then here you'll end up with 6, 7, 8. So that's another way to think about it. If you're doing a permutation, it evaluates the same as 8 times 7 times 6. So up to you to decide if you like this way of counting better, or I guess this, yeah, I don't know. You can also code it out in Python if you want. But yeah, remember that this is the number of ways to arrange k out of n items, where k is the number here at the bottom. Sorry, n minus k is the number at the bottom, and then n is the number at the top. All right, so that's permutations. There's one more counting method known as combinations. So in combinations, it's kind of similar. It's the number of ways to choose k out of n items. However, in this case, the order of your items doesn't matter. So very, very similar setup. If I have a collection of 8 seashells and I want to randomly pick 3 to give away, how many combinations of 3 shells are there? That's the same thing as saying that, okay, in this scenario, song set ABC is different from BAC. Sorry, it's the same as BAC. So intuitively, if we're counting this way, your number should be bigger than if you're counting this way, because in this way, any combination of 3 that are the same like ABC, no matter what order they are in, it counts as the same. I hope that made sense. In this case, just think we're picking 3 seashells. The order of seashells doesn't matter. I'm just grabbing 3 seashells and giving it to someone. The formula is slightly different. And because the number is intuitively smaller, you're actually dividing by more. So the formula here is we're taking n factorial, dividing it by the product of k factorial and n minus k factorial. So we're adding something extra at the bottom. So to just draw it out, for permutation, for permutation, it was, hold on. I was trying to draw it out. Okay, there we go. So for permutation, the formula is n factorial divided by n minus k factorial, where for combination, it is n factorial divided by k factorial times n minus k factorial. So therefore, the combination usually gives you a smaller number. It's very often that it's confusing whether you should use a permutation or a combination. Like I honestly have to sit down sometimes and really think about which one I'm using. I sometimes use this to help, like, okay, should the number be bigger or smaller? Am I counting repeats as numbers or not? So in this case, with the same numbers, picking 3 out of 8, the answer that we get out of here using this formula is 56 instead of what it was 336 earlier, I think. Yeah, before it was 336, and now it's down to 56. So with these 2 different counting methods, you end up with different numbers. All right. Any questions about any of these counting methods so far? Cool. I will tell you now that when I was in college, 1 week was spent talking about permutations. The next week was talking about combinations. So we are going through a lot all at once. So if a lot of this is like, whoa, a lot, that's very normal.
I got
Okay.
a quick question.
Yeah.
So is that like a rule of thumb that combinations are less than permutations? Is that like a...
Yes, always. If you're dealing with the same numbers, combinations is always going to be smaller than permutations.
Okay, thank you.
You're welcome. Okay, next let's talk about conditional probability. This is going to come back with one of our machine learning models later in like phase 3. So this is the one that's probably, it's more of like the way that you think about probability, not so much formulas again, but there are formulas to calculate it. So the conditional probability is the probability of something occurring given that something has already happened. And so this is an important concept for Bayesian statistics. One of the models that we'll be working with is going to be based off of Bayesian statistics. And Bayesian statistics is basically this statistician called Thomas Bayes. He came up with this whole idea of like, okay, why should I just use that idea of probability where I should do something like an infinite number of times to think about probability versus can I just take in whatever information I already have to determine probability? As an example, let's say that you're rolling a six-sided dice and 3 times in a row it's come up as 6. Because of that, just by I don't know if you've ever rolled a dice a bunch of times and a 6 has come up 3 times in a row, you know that the probability of it being 6 again is much less likely than it was before, right? And so that's the kind of intuition behind Bayesian statistics, the fact that you should be able to take in other information in calculating your probability. We'll get way more into detail about that later on, but that's where that thinking comes from. And so what is the probability of A given that probability of B? Wait, hold on, let me rephrase that. The way that you denote conditional probability is with that vertical line. So over here, this just means what is the probability of A given that B has occurred? So what is the probability of A given that B has occurred? And the formula for that is actually probability of A union B. Oh, actually, no, it's not union. Let me undo that. It's A intersect B divided by the probability of B. The idea of this is B has already occurred. So here we have A and B. So this one is A, this one is B. Let's just say that B has already occurred. What proportion of B is A? That's another way I like to think about it. It may or may not help in like understanding conditional probability, but I like to think of it as what proportion of B, because B has already happened, is A. And so it is this section in the middle as a ratio of, let me use a different color, of this entire circle. So to just throw some numbers, let's just say that we had our example from before. We have our 1, 2, 3, 4, 6 example, and we have our 5 over here. What proportion of B is also A is 1 out of 3, because we're only looking at B. We're zooming in on B now. And out of this B, 2, 4, and 6, 2 also belongs in A. So that gives us 1 out of 3. If we look at it from a formula standpoint, kind of similar. Probability of A intersects B, which is 1 out of 6, divided by the probability of B, which is 1 out of 2. If you do out the math, it actually does come out to 1 out of 3. So that's how you can think of conditional probability. I like to think of it as zooming in on what has already occurred and then figuring out this probability here. There's this formula here. Whenever you are posed with a conditional probability question, they usually give you the formula. So in your labs, you will have the formula with you if you're working through those questions. All right, questions about this, because it's about to get a little bit more complicated. Okay, well, the next thing is the last thing that I wanted to talk about, and it's the law of total probability. There's a formula for this, and let me see if I can write out this formula in, let's see, there's a text box here. Okay, cool. So this diagram down here, we have a sample space that is actually made up completely of different A's. So there's A1, A2, A3, A4. Superimpose on that, you also have B that is just occurring on top of that. So if you want to find, let's just say that you know the individual conditional probabilities, and there are circumstances where this happens. And I'll give you all an example of a question like this in a little bit. let's say we know the probability of B given A1, B given A2, and B given A3. That means that we know what proportion of A1 is also B. We know what proportion of A2. We know what proportion of this entire rectangle here is also in B. And we know what proportion of A3 is in B here. So we know these proportions, but we don't know what B is. If we know those proportions, law of total probability says that we can actually calculate B. And it says that B is the sum of the individual conditional probabilities, given that each A segment is disjoint and no part of B that isn't part of, and no part of B, there is no part of B that isn't part of an A segment. So in this case, the formula is actually, and don't worry about memorizing this for now. It's ingrained in my head because I did this for like years, unfortunately, but the probability of B is actually equal to probability of B given A1 multiplied by the probability of A1, and then plus the same thing for A2 and A3. So plus probability of B given A3, probability A3. So this, if you don't know B, but you happen to know these specific conditional probabilities, you can calculate B. I know it seems pretty far-fetched, like why would you not know this middle section, but know like the specific proportions? Any questions on this before I get into a specific example to show where you would use this? Okay, so the specific use case for this, and let me drag in something real quick. I want to drag in, hold on. Let me look for the resource real quick. Okay. So let me do this. This is, oh, let me clear my drawings first. I'll send you all a video that has me walking through all of these questions step by step. The question here is, let me see if I have it here. Law of total probability. Oh man, it's not in this one. Okay, never mind. I have it somewhere else. Give me a second. Here. Okay. That one I thought had the solutions, but this question over here, let me zoom in a little bit. Actually very, very relevant. And of all of these questions, this is the one that comes up the most. So this is a scenario. Let's just say that the COVID test has a 10% false positive rate and a 5% false negative rate. Given that you've tested positive for COVID, what is the probability that you actually have the virus? And assume that 5% of the population has the virus. This question, even though it looks like there is like not like a circle and squares going on like this question is actually one that you will use the law of total probability to solve. I think, oh, okay, yeah, I'll talk about this question when we get to section 17 because we get more into the Bayes theorem then. But yeah, I'll get into how you would solve this using the law of total probability in a few weeks' time. But yeah, just so you all know for now, this law of total probability, not important to remember in terms of like definition or anything, just know that it exists. And if you see a question like this, you will have to think about the law of total probability. But also you'll see that when we draw out the probabilities, then it'll get more and more intuitive. Cool. Well, that was the last thing I had to share. Just a heads up, the next few, I think the next two, 12 and 13, I think are already on the repo as well. If you just want to see what's coming up, is going to be statistics and it's going to be pretty hardcore theory. But I will mention which are things that you can gloss over, which are things to remember. So not to worry about that. But yeah, that's all I had to share for today. Does anyone have any questions? All right, I want to make it very clear that this was like pretty much an entire college semester's worth of material that you are literally absorbing in like half a week. So I understand that it's a lot. If you just get the rough gist, I would say that as you're reading the material, if you understand what you're reading, that should be good enough. The coding exercises, the labs in this topic and the next couple of topics as well, honestly, not the kind of coding that you'll be doing as a data scientist. So if some of the coding, they have you set up formulas and such, which is honestly good practice for translating math into Python. But if you're having trouble with that, no worries, you can just ask me and we can work through it together. All right. That's all I had to share for today.